Tolerance is a term we sometimes hear in engineering, and it has to do with the amount of error that is acceptable in the dimensions of a part or a product. In this lesson, we're going to learn about tolerances and what they have to do with engineering design. We're going to find out what a tolerance is, what the different types of tolerances are, how to calculate a tolerance, and how we can use tolerances in CAD when we dimension a drawing. It's important to realize that all parts and products vary somewhat in their measurements. Even when an item is reproduced thousands of times on an assembly line, the parts won't be perfectly identical. When measured to a high enough precision, we find that variation exists within all parts that are supposed to be identical. The question is, how much variation is acceptable for a part to fulfill its function? It depends on the application. For example, in constructing a building using wood frame construction techniques, pieces might vary as much as 1/16 of an inch without causing a problem. But in a different application, like the precise inner mechanism of a wristwatch, the pieces are super tiny, and being off by 1/16 of an inch would be completely unacceptable. In this application, an acceptable tolerance might be as small as 1/10,000th of an inch. It all depends on the application, and skilled engineers need to understand when and how to apply a tolerance to their designs. As I said, a tolerance is an acceptable amount of dimensional variation that will still allow an object to function correctly. There are 4 basic types of tolerances found in technical drawings, including limit dimensions, unilateral tolerances, bilateral tolerances, and general tolerances. We're going to take a look at each one. The tolerance of a dimension is an actual numerical value that can be calculated. So if you're ever asked, what is the tolerance of this dimension, the answer is a number. It's the difference between the upper and lower acceptable limits of a dimension, or in other words, how much the dimension can vary. For any given example, subtract the lower limit from the upper limit, and the result is the tolerance for that dimension. In this example, the smallest the hole can be is 0.25 inches, and the largest the hole can be is 0.28 inches. So the tolerance of this dimension is 0.03 inches. The first type of tolerance we're going to learn about is called limit dimensions. This provides an upper and lower limit for the dimension, and any size between or equal to the upper and lower limits is allowed. Now that you know how to calculate a tolerance, what is the tolerance of this dimension? If you said 0.01 inches, you're right. 12.755 inches minus 12.745 inches equals a tolerance of 0.01 inches. We can easily add tolerances to our dimensions in Autodesk Inventor in a few different ways. The only thing that makes this a little tricky is that Inventor sometimes uses different terms for things than what we've discussed in class. That's okay. It's typical to see different terms for the same thing used in education and in industry, and it's good practice to be familiar with both. To apply limit dimensions to a drawing, use the standard dimension tool as you normally would, and when the Edit Dimension window appears, click over to the Precision and Tolerance tab. Here you will find a list of several different tolerance methods you can use in your drawing. The one we're looking for is called limits, and you have the option to choose limits stacked, which will place the upper limit stacked on top of the lower limit, or linear, which will display the limits in a straight line. When the option is selected, you can individually change the maximum and minimum values for the limits, and click OK when you're satisfied. The next type of tolerance we're going to see is called a unilateral tolerance. A unilateral tolerance allows variation in only one direction. For example, if a peg must slide into a hole, it might be acceptable for the hole to be slightly oversized or the peg to be slightly undersized. But if the hole is too small or the peg too large, it could cause the parts not to function. A unilateral tolerance uses a plus and a minus sign to communicate whether the dimension is allowed to vary up or down. What is the tolerance of the hole in the picture? If you said 0.02 inches, you're correct. The base dimension is 0.675, but is allowed to be as much as 0.02 inches larger. However, any dimension smaller than 0.675 would be unacceptable. To create a unilateral tolerance in Inventor, place your dimension as you normally would, then click the Precision and Tolerance tab in the Edit Dimension window. Under Tolerance Method, select Deviation. This option lets you set a different upper and lower tolerance range. For a true unilateral tolerance, one of these options would be left at 0 and the other changed, but certain situations might call for an asymmetrical tolerance with different numbers entered in the upper and lower ranges. A bilateral tolerance is a tolerance that is allowed to vary a certain amount in either direction. They use plus-minus notation to indicate that the dimension can go up or down by the specified amount. In this example, the dimension is 2.632 inches, give or take 0.03 of an inch. What is the tolerance of this dimension? This one's a little trickier. If you said 0.03 inches, you would be mistaken. Remember that the tolerance of a dimension is its upper limit minus its lower limit. In this case, the tolerance is 0.06 inches, 0.03 above the base value and 0.03 below. To create a bilateral tolerance in Inventor, place your dimension as you normally would, then click the Precision and Tolerance tab in the Edit Dimension window and select Symmetric from the Tolerance Method list. This option allows you to enter a single range that your dimension can vary above or below the base dimension value, and indicates this using plus-minus notation on the drawing. The other way that tolerances are expressed in technical drawings is through a general tolerance. A general tolerance is a note on the drawing that indicates a tolerance for all of the dimensions. This eliminates the need to report a tolerance on every single dimension of a drawing. It's important to note that the general tolerance states, unless otherwise noted, which means if a dimension does report its own individual tolerance, this overrides the general tolerance for the drawing. The last tolerance method we're going to look at in Inventor is the general tolerance, which is as easy as creating a text note on the page with tolerance information like this. A general tolerance will often include different tolerances for dimensions expressed at different precisions. It looks like this. When the dimension is reported on the drawing to 2 decimal places, it will have a tolerance of plus or minus 0.05 inches. When the dimension is reported to 3 decimal places, it will have a tolerance of 0.005 inches. Of course, all of this is only true if the dimension doesn't specifically state a different tolerance. When establishing tolerances for a part, there's an important balance that the designer needs to consider. Precision comes at a cost. If the tolerances for a part are too large, it can affect the functionality of the parts. The parts might fit together poorly when assembled, which is a common characteristic of low-quality products. However, if tolerances are too small, it can affect the cost of the parts. Parts with high tolerances require more precise machinery to manufacture. More quality control inspections may be required, and more precise measuring tools might be needed to perform them. It's the engineer's job to understand what level of tolerance is necessary for a part, and to not set tolerances too loose or too tight. So how did you do? You should now be able to answer each of the questions that we started with. In class, we're going to see if you can read, understand, and use tolerances on your own. Go back and take another look at the lesson if you need to. Thanks for watching. Good luck.